Um, so graded homework is there. So if you submit by hand, please pick the homework set over there. And then be careful about the camera position. Okay, I hope it's okay. And then as always, please refer to the updated homework, no, updated lecture note. So you have a link, right? So please tell me. I spent a lot of time to write this lecture note. So, and then there must be. I didn't print out this part. No. Okay, so last time briefly explain about the idea of renormalization. So here you start with so-called bare Lagrangian, and then as I mentioned, there are lots of quantum correction to the field itself. So for instance, if you have propagator, so you have of the experiments, you have something like this one. This kind of diagram, and then this kind of diagram, and so on. There are lots of quantum correction that will change the propagator from, will give you the, at the end of the day, so you get that propagator will look like this way. Like this way. So therefore, it's better to incorporate this, the change into the field itself. And then rewrite everything. So I just omitted R here. So the implicit there's the R here, everything R. And then can you see the blackboard from the back, or it's better to close the curtain? Is it okay? Is it okay? No problem? Okay, and then so here, so the Zi is split into 1 plus delta I. 1 plus delta I, and this delta I has lots of encode. So for this one is called counter term. Counter terms, and it has the quantum correction, encodes and information quantum correction. So this is called so-called UV. So it's a Lagrangian at a very high energy, so that the experimentalist cannot detect what's the value of M0 or E0 because energy is too high. But in our energy level, or even experimental level like MEV, so whatever, people just using whatever KEV, MEV, GEV, and TEV, next is TEV. The LIT has the magnitude of TeV. Tera and G is giga maybe. Anyway, so it's you know, right? So it's kind of memory. If you buy external drive, and so it's just 1 megabyte or whatever terabyte and so on. And you get familiar with. So even if you go down to that energy level or whatever, so usually maybe MeV and so on, 100 MeV and so on. So you can measure the value of E and M. So these are the really physically measured value of and physically meaningful parameter, mass of electron, charge of electron. And the difference between UV, this is called UV, and IR, I will explain what it means. So the high energy Lagrangian and the low energy, our experimental level Lagrangian. The difference is pushed into this content. That was the idea. And then we will evaluate this value of Z and counter term explicitly so that how this M and E are also receive some quantum correction. So that's we are going to see. We are going to learn from now. In QED. Okay. And the first step is at the this Z1. So first step. So first step is the first step. So we will do step by step. Z1 first. We determine Z1 first. Note that so Z1 appears as the following. So let's see. So Z2, Z3 start 0 is equal to Z1. So that's how they are related. Z1 and then Z2 and 0 is related to M plus delta. So that's the relation. And then, so we will do step by step. So we first start determine Z1 first, next is Z2 first, and then at the end of the lecture we will determine Z3. That's the step. And today's calculation is very much involved, so that most likely you will get lost if you don't concentrate it. So that I just give you first very involved, but you have to get used to it. If you want to, I mean, most of the quantum physics 1, I guess, do not introduce this detailed calculation. I mean, because of lack of time. But it's better to do that. And this is the most important calculation, K and K prime, which is K plus Q. And as you can easily see, so here P minus K is this one. So we would like to evaluate this one. And this is related to anomalous magnetic moment. So this bar diagram is related to this anomalous magnetic moment. As I introduced at the beginning of the lecture, so this is the one of the milestone in the early the first half of the physics. First half of 20th century in physics. And this is related to anomalous magnetic moment. I will explain what it is, and then so usually you have this kind of stuff is related. So as I mentioned, so this is a quantum correction to the vertex of this one. So here we assign this is equal to, so if you have a whatever, mu, so this is assigned, we just gamma mu, I in tree level. We just assign final row. Final row, this one, is this one in QED. So coming from here, this part. But here, so we see the correction to this side, the quantum correction. And then, so we try to evaluate the boundary diagram for this one, and you just apply the final rule. So now we have the K can take any momentum. K can take any momentum, so therefore you have to integrate over. So first, and then first we have the propagator. The propagator, this one, propagator, let's spot. So this is very involved calculation. So K minus P square plus I extra. So often, so in my notes, I already omit the I extra because I'm lazy enough. And then U bar of P prime, and then minus I, and then I. So therefore, this is mu, and this is rho, I think, rho, and this is mu. And then, so, okay, let's do step by step. So this propagator, yellow propagator, is this guy. And then we have the propagator ferment. So this is the diagram, and of course unfortunately, what kind of color I can use? Maybe orange. So this guy, this propagator, corresponds to this guy, and then pink. I already used pink. Bear with me. I use the purple. Is this guy. And then of course the so this point corresponds to this one. I mean, most likely you guys already get used to it, but some students maybe. Oh, sorry, it's not. This is not epsilon. This is p. And then this vertex is coming from. Okay, so that's the meaning of the meaning of this Feynman integral Feynman diagram, and the goal is to evaluate this integral today. Okay? And it's very involved, so it's a very involved competition. I will give you a strategy. First of all, we will introduce so-called first step is Feynman parameter, and then to perform this integral, you need to introduce lots of tricks. The first trick is so-called Feynman parameter. Second, we will do the so-called Wick rotation. Okay, and if you try to perform the integral, because I mean schematically. So when K is the momentum of this internal Feynman Dirac field, but if K goes to it's become high momentum, which means that this diagram becomes very so this loop, there's a loop here, but the K is high enough means that since the Heisenberg's uncertainty principle, if K is equal to h bar, whatever. If it is big enough, x becomes small. Okay. So therefore, this diagram, if k is very big, means that this group becomes very becomes small. Okay. And at the end of the day, it shrinks to the point. That will give you so-called infinity. So this infinity, UV divergence, is called UV divergence, is actually pushed into this counter term, this counter term. So this infinity is really coming from the UV high energy Lagrangian, bare Lagrangian, and then the Lagrangian in our scale. So therefore, this infinity is just cannot be measured by experiment. So what we are looking at this guy, this guy, the difference between high energy Lagrangian, which we don't know what it is, we cannot measure. And then those difference is really pushed into the difference has the infinity. And that is pushed into this counter. That we will see that. And to this kind of trick, there are lots of ways. So the first we will do Pauli, Euler's regularization. Did I write the correct spelling? Pauli, Euler's. Oh, magically, my spelling is correct. And then after that, we would do that so-called renormalization or counter term. How to get rid of this infinity. Okay. So that's a step. We will do that. Okay. So the calculation is lengthy. So we will spend hours to evaluate this integral today. Only one integral. This class. But it's very involved, so we will do the step by step, then we will need to be careful about the calculation. So you get easily lost if you just don't understand the strategy. So be careful. So you have to be concentrated today. You have to, yeah. Otherwise, yeah, you will get lost in the huge calculation. Okay. So this can be just if you use. Let's see. I also have my own note for detailed calculation. Let's see. So I'm going to omit the plus epsilon from now on. I'm going to omit plus epsilon because it doesn't play any role in this calculation. So this can be understood as the minus IE square and the d okay 2 pi to the fourth, and then k minus b square, and then k square minus n square, and then e minus k, k square plus k prime minus n square. So this is the denominator, and the numerator has the u of p prime, u of p, and then numerator is something like a gamma nu, and then like this. So, and then now, so we use the following trick. So we know already, I mean, A slash B slash, I mean, just crippled algebra. You just use crippled algebra, A of B minus B slash, A slash, and also gamma nu A slash is equal to 2A nu minus A slash gamma nu. So you have to use this kind of and also we need to use the lots of trick. Let's see. Then at the end of the day, so what we have is that just a moment. So in this step, so let's do one by one. B square, 2 4k, 2 pi to the fourth. And then U bar of P prime, and denominator is same, so I'm not going to write the denominator. So we are interested in numerator, only numerator. And then what we have is that the 2 times k slash k nu, prime nu, k prime nu, and then minus k slash. So first, I just bring this gamma nu into here. Okay. Gamma nu to here, so we will get the minus m k prime, and then let's see, gamma nu. So I just bring this one to the left, and you need to use the this row. Okay, you need to use this row to bring this one. And then you have the gamma mu, and then you have the same similar. So bring this one into the left, and what you get is the 2k nu minus gamma nu k slash minus m, and this, and the up. So the denominator is same. Okay. And then unfortunately, so I'm going to erase here because I want to continue here. Okay, and then so we'll use this kind of identity. So gamma gamma mu. So if you use the threefold algebra, this will give you minus 2 times gamma mu. Okay. So if you apply this rule into this gamma nu, so then what you get is that you have a orbital factor 2 times I e squared equal k 2 pi to the fourth p bar p prime. Again, I'm not going to write the denominator because it's the same. And then what you end up with that the k slash gamma mu. So here k slash coming from this one, k slash gamma mu, and then k prime slash coming from here, the contraction here. Okay. Here, and then plus m squared gamma mu. So this is coming from, m squared is just m times n here, and then you apply the gamma mu is minus 2 times gamma mu. Okay. Sorry, it should be output. Sorry, I think my lecture notes was a typo like this. Yeah, output. It should be output. And then you have minus 2n k plus k like mu. Okay, so that's what we have for so here, so we just again apply the gamma mu is this guy, and then you have again apply k prime and the gamma mu and the k slash k prime slash gamma mu k prime slash, and you get this. I think my explanation is not correct. Sorry. I forgot. I made a mistake. Sorry. So k slash gamma mu times n. Sorry. So this will give you this term, and then k slash gamma mu times n will give you this term. Yeah, I also make a, so you have to be careful about when you do this kind of computation. Okay, so this is a case. And then, so what's left? So this guy times this guy times this, this guy times this guy times this guy times this guy will give you this one, and also the same as here. This guy times this guy times this guy times this guy will give you this guy. What did I miss something? Yeah, I think so. So we need to do this guy times this guy times this guy times this guy times this guy, and that should also give you this guy. And you have to be careful of coefficient, and the overall factor is plus 1. And the m square is just, of course, this just multiply m square, and then you just multiply this guy. Okay. And the cross term is the m times, what was that? This k, and also m times this k. So you have to be careful. And if you manipulate this one, you can easily run into this if you use this one. So that's the case. And we want to perform this integral, so we haven't get to the point of Feynman parameter yet. Okay, so before introducing Feynman parameter, so let's use some guess. We can just narrow down. Okay, so I call this one is equal to. I call this one is equal to u bar p prime delta gamma mu p prime p and then u of p, and where delta gamma mu is equal to gamma mu plus delta gamma mu. So that's the expression. So leading orders, as you know, so times IE maybe, times IE. So leading order is just ordinary gamma matrix, gamma mu. And then this delta gamma mu is the order alpha. Order alpha. Order alpha means alpha is of course the alpha is equal to E squared divided by 4 pi squared. So E squared already appearing in here. E squared already appearing here. So since you have a 2 vertex, so it's just an order alpha correction. So that's delta gamma. So this delta gamma is the first quantum correction to this vertex. And then the form of gamma mu by Lorentz symmetry, Lorentz invariance. So the gamma mu, the most general form you can obtain that so this vertex should be determined by P prime and P. So it should depend on, of course, Q is equal to P prime minus P. So therefore, this vertex is essentially should be determined by the function of the incoming momentum and final outgoing momentum. Therefore, so the Lorentz invariance means that it should depend on the function of gamma mu, which is A plus B P mu. Maybe I call it D plus F A B C D E P prime. So it should depend on the P and P prime, and then Lorentz invariance, and also there may be proportional to some classical, and then some quantum correction will give you some number. There is a possibility. In any case, D and E are some numbers. In any case, the Lorentz invariance tells you that this should be four vector in Lorentz transformation, and then it should depend on P and P prime. So therefore, we can just write down that just the most generic form of this gamma mu is some function of P and P prime, and also it should be depends on gamma mu. Okay. And then, so we can just manipulate this one into the following form. I mean, just a linear combination. C minus B prime. Okay. And then we know that for the diagrams, as I mentioned last time, so in word identity tell you if you contract with gamma mu is of course the mu is the current here, and if the photon has a vector, so therefore if you contract with the momentum of photon, it should be equal to 0. It should be equal to 0. So therefore, so this means that if you contract, so this means that the C has to be 0. So this means that so if you contract with Q is of course is equal to P prime minus P mu and mu. So therefore, if you contract with the P and P prime with this one, this is automatically 0 because I mean it's just P square minus P prime square is equal to just a 0. On the other hand, here this is no longer 0; it just gives you square. Q can take take any values, any momentum value because it depends. So therefore, this means C equals to 0. C has to be 0. Okay. So this And also, so we have a so-called Gordon identity which you derive in the form of Gordon identity. Which is the U bar P prime, gamma mu, E of P is equal to U bar U prime plus, P prime mu plus P mu divided by 2m plus I sigma mu nu and then Q nu and 2m and then U of P. So this is the so-called Gordon identity. Therefore, if you sandwich gamma mu, if you have a P prime plus P prime some P sandwiched by U bar and U, which can be written in terms of gamma mu and then sigma mu. And then sigma mu nu is defined as just a commutator of the gamma matrix. It's like this. So therefore, so C is equal to 0. C has to be 0. And then yeah, I mean, so one may wonder that the YA is not 0 once you contrast Q dot A. But if you just gamma mu is of course contract with the U of P. So we know the P slash acts on U of P is equal to M U of P because of plane wave, and the P prime acts on U bar of P. You have the same equation. Let me write that. So this is equal to 0 because I don't have a space to write down. So P slash of UP is equal to MUP, as you know, and P slash prime U bar of P prime is equal to M times U bar P prime because of the equation motion. So therefore they count down. So Q is P prime minus P. So therefore this is equal to. So this one you don't need to worry about, but here it's not 0. So therefore you have to set equal to 0. And now, so using Gordon identity, we can write down P plus P prime into the following way. So therefore, at the end of the day, so we can just write down gamma mu of P prime of P is equal to something proportional gamma mu plus something proportional to sigma mu nu and then Q nu divided by 2m. Okay. So everything written P prime plus P is written linear combination gamma mu and sigma mu nu times Q. So therefore, and this coefficient I call it A and B, but it should be function of the Q square because of Lorentz difference. And this coefficient is called I call it the F1 and F2. So instead of A, I wrote A and B, so I just rewrite F1 and F2. So this should be the generic form of the and we will see that if you do this integral, literally one can manipulate this integral into this following form. That's I'm going to show that. And we will read off this F1 and F2. And this F1 and F2 is called famously called, this is called form factor. Of electron. Okay. So yeah, and but by performing this integral, we will determine F1 and F2 from now on. Okay. And why it has to do with the anomalous magnetic moment is that, as you know, gamma mu is modified. Gamma mu, if you incorporate the quantum correction, is modified as this capital gamma mu. So therefore, Dirac-Lagrangian, L Dirac-Lagrangian, if you incorporate the this quantum correction, psi plus E. So if you go to low energy, so you can set Q square equal to 0. So therefore you have a mu. So you can just write down like this if you modify. So the gamma mu has the so-called the proportion of some coefficient in front, f1 q squared equal to 0. And also you have additional term. Of course, derivative. So mu is really mu is this wiggle line which has momentum q. So this momentum q is the just you can just apply the derivative, you can get this q. So therefore, the Dirac-Lagrangian is modified like this way. And as you did in the homework, so you just take the non-analytic limit. But if you do when you try to do the non-analytic limit, first you have to do square the Dirac equation, and that will give you this kind of equation. So if you square the Dirac equation, so this is square as you did in the homework. So square of Dirac equation will give this one, and then what's relevant is this term, form of anomalous magnetic moment, as you did in the homework. I mean, if you forget about it, you can just take a look at the solution of or you just review your homework. This will give you the anomalous magnetic momentum, and then this will give you G is equal to 2 plus G F2Z. F2Z. So therefore, this is a correction to the anomalous magnetic moment. So 0 means I take Q square equal to 0 because we want to go to low energy. So which means that the P and the P primes are almost same. P and P primes are almost same. So that's the non-relativistic limit you can take. And this is the anomalous magnetic moment. So this is the anomalous magnetic moment. Okay. So therefore, this form factor is literally related. Literally give you the anomalous magnetic moment. So that's the yeah. So our goal is that they perform this integral by using final parameter weak rotation, Pauli-Villard regularization, renormalization, and determine F1 and F2. And in fact, renormalization only. I mean, F1 needs renormalization. F2 is just UV finite. It doesn't have a divergence. And then, so we determine this. We go through this step, determine F1 and F2. That's the goal of this lecture. So it's going to be very involved calculation. You have to have a strong mind to perform this integral. Okay, so let's first talk about the final parameter. Let's see. I want to keep this thing, and I can erase. Okay. Let's see this so-called final parameter. So final parameter means that the care about this denominator. So final parameter is as follows. So you have, if you do this kind of loop integral, you always have the propagator in the denominator. So you always have this kind of factor. And this is the 0, 1, you can show. So this is the case, and so this is the identity I'm going to use. And in fact, so this can be shown by induction. In fact, n equal to 2 case is super easy. Or we can just easily show that the a1, a2 is equal to d x1, d x2, delta x1 plus x2 minus 1 is 1 over x1 a1 plus x2 a2 square. And this is super easy to do that, because I mean, once you perform x2 integral, if you perform x2 integral, you just impose x2 is equal to 1 minus x1. Therefore, this is equal to and then by change of variable, so this can be set something like this way: 1 over a1 minus a2 square dz over z square, and a1 minus a2 minus a1 minus a2. Sorry, it's hard. So I just set this inner. Oh, sorry, I think I should write down the integration range. 0 and 1 and 0 and 1, and then what I did is that the so let's see. What I did is that the z is equal to x1 a1 minus 1 minus x2 x1 a2 divided by a1 minus a2. That's what I did. So then, so just plug this one into here and just do that. Just ordinary change of variable for integral from so you can bring the upper one to the lower one. Okay, upper one to lower one by changing this kind of variable. Okay, and then the performance of this integral is super easy. Of course, this will give you in fact this one. You can easily check that. I mean, do you want me to do that? I mean, you can easily check that. I mean, dz over z square, if you do the integral, you get this one, right? Is it correct? Minus 1. And then plug a1 over a1 minus a2, and a2 over a1 minus a2. And plug this one into here, you can show this is equal to 1 over a1 times a2. So this is super, just elementary integral. And then if you want to go to the upper one, you have to do the induction. So you just assume n minus 1 is correct, and then you just multiply this one, and you just do the same trick, same trick of what we have done in any given two cases. By induction, one can show this. And the final parameter, logical final parameter is that this xi, these x variable xi are called a final parameter. Final. Okay, so now we want to apply this final parameter into this denominator, this denominator. Okay. So, which blackboard I should use? Maybe this one. I can erase this one. Okay. Anyway, everything recorded, so it should be okay. Let's see how many people. Okay. So if you apply final parameter denominator, so denominator is equal to the x k squared minus n squared. So this is a1, I call it a1, and a2 is next one. So like this way, denominator becomes like this. As you can easily see from here, so now n equals 3. So you have this 3 denominator. I call it a1, a2, a3, and then xy is x, y, and z, and then to the cube. So essentially what we have is that the denominator is, so we want to write down this one is equal to integrand d cube, some numerator. And d cube is cube coming from this n equal to 3. Okay. Is it okay? And then x times this guy, y times this guy, and z times this guy. And then the d is inside here. And then we'll do the integral. It's a boring thing, but they have to do. Okay, let's. Yeah, this kind of calculus I also get easily lost, so let's do step by step. So we know that the k prime is equal to, this is equal to k plus q. K plus q? Yeah, k plus q squared. From this diagram. And just, so just expand it. Sorry, yeah, it's okay. Expand it. So then what we have is x plus y plus z to the k squared. So you have, oh, sorry, there's no square, sorry. Be careful, there's no square here, sorry. So I just expand the k plus q squared, and you have a k squared plus y, and the k squared plus z times d, and the x plus. And then what you have is the y q squared, that comes from here, and then plus 2y k dot q plus z so m squared is just x up here, and also, sorry, I don't understand why the plus sign here. You should point me out. It should be minus, sorry. So minus. I'm sorry. That's my sorry. So m square up here and also square here. Sorry, there are lots of mistakes in here. M square up here and here, so you have an x plus y. And then we can just write down this one. So x, y, z is equal to 1. X plus y plus z equal to 1. Okay. So therefore, this is equal to k squared plus 2k go to yq minus cq plus yq squared plus z squared minus x plus y x squared. So that's the case. And then you do the so-called Gaussian, how to say? What is it called? Gaussian, blah, blah, blah. So you define, so from here to here, I use x plus y plus z is equal to 1, of course. And then we define L square. L is equal to k plus y q minus dp. And then this would, so you define like this way, so this one is become like this way. L square minus how much do you want me to be specific? How much do you want me to do calculation explicit? I mean, I can just do all the calculation for you, but it's going to maybe it's going to bore you. Do you want me to do each step or skip? Can you fill out the detail? Which do you prefer? Do you want me to do each step? Please raise your hand. I can skip some step. I can skip some step. Okay. Oh, this is majority. I don't need to explain any step. Okay, I'll skip some step in that case. So the reason why, so the reason why I introduce L is equal to k plus this one is that if you do the L square, you cover this part. Okay, L square cover this part. So therefore, you have to minus this one, y q minus dp square, and then plus yq square plus dp square minus x plus y plus m square. Okay, and I call this one is equal to delta. So I call this one is equal to delta. Delta, I already omitted plus epsilon. I'm not going to write down plus epsilon, so because I'm lazy. Okay. And then you can just do the manipulation. So delta and the equal to, so I mean you can just do the manipulation a lot, and then yeah, I'm not gonna explain. So you mentioned, the majority of people mentioned that I don't need to explain all the detail. 1 minus d squared m squared. So I call this one is equal to delta. I go delta. From this step to this step, you have to use p squared equal to m squared, and then p one has to use this step. I mean, it's a good exercise from top to bottom. I'm not going to explain all the detail. So you should fill out the calculation. Okay, now, still I'm in processing number 1. So, Okay. So now, we already write down. So the denominator is d is this L minus delta cube. Okay. So we now this part can be written as the denominator is L square minus delta cube. That's already great simplification. Okay. Already. Now we try to take care of this numerator. And numerator is this guy. And we need to rewrite everything in terms of this L. This L. Okay. Okay. So numerator is equal to u bar p prime. And so here. So I'm already reached to this part. It's the k slash gamma mu k slash prime plus m square gamma mu 2m k plus k prime yo. Okay. And now we would like to write down everything in terms of L. To do that, u bar or p prime, and then here what we need to do is that the L slash minus y q slash minus p slash gamma mu, and the k, as you recall, k prime is equal to k plus q. Therefore, it should be L slash plus 1 minus y q slash minus p slash plus m square gamma mu. And then what we need to do is that the minus 2m, and here what we I think I missed mu here. So what we have is the so this is 2k, so this is 2k plus q, right? And we know k is equal to this guy. So therefore 2 times L minus 2 times yq minus p plus q. So therefore this is plus 1 minus 2y q plus p minus p, sorry, minus p, and then times u. Okay. That's the case. So I just rewrite everything in terms of L and then Q. And now we notice that the following. So now dk integral is become dl integral. To pi to the fourth, and denominator is d to the cube. If you have L mu, so if you take L goes to minus L, this should be equal to, if you take L goes to minus L, this becomes the integral minus d for L to the 2 pi to the fourth L mu dq. Okay. So dq in the denominator it's just even, and then numerator is odd. So therefore, if you go to L goes to minus L, you get the minus sign, overall minus sign. Okay. So therefore, this should be equal to 0. Okay. Something equal to minus something, a equal to minus a is equal to a has to be 0. So this is it's because the numerator is odd. And also, if you have dql, d for L, 2 pi to the fourth, dq. The same reason, if mu and nu are different indices, I think it's not p, d. Mu and nu are different indices. For instance, whatever 0 and 1, or whatever 1 and 2, different indices. That you can perform the same trick. So for instance, if you L0, L1, you can set L0 to minus L0. Only L, then it becomes minus of this one. So therefore, if mu and nu are different, the integral is 0. Okay? So therefore, mu, non-zero power coming from mu is equal to nu, indeed. Okay? And the Lorentz invariance will tell you that it's symmetric, and it should behave as the Lorentz invariance tells you that this should be equal to something proportional to 2 pi to the fourth. It should be proportional to G mu nu by Lorentz invariance. It's symmetric tensor, second symmetric tensor, and diagonal is non-zero, which means it has to be equal to G mu times L square divided by D to the cube. Why that? If you contract with, so let's look at that, and there's some powers, there's some constant. So why that? So if you contract with L nu dot L mu, so you should get L square L mu. Okay? And if here also the same. So you should get the L mu, so G mu nu, L square dot L mu, you get the L square L mu, okay? Like this one. So all the Lorentz invariance will tell us that this should be proportional to G mu nu times L square. And if you take a trace, in the numerator, if you take a trace, let me erase. If you take a trace of this one, trace of L mu nu, and nu, this is equal to, trace means mu nu, so which means the L square. On the other hand, if you take trace of G mu nu, L square, then what you get is that the trace of G mu nu is indeed L square plus times 4, right? G mu nu trace is delta I, delta mu mu, which is equal to 4. 1, 1, 1, 1. Okay? So therefore, if you take trace, it's the 4. You get the 4. So therefore, so the gap between L mu nu and G mu nu L square is 4. So therefore, one has to divide it by quarter, multiply quarter. It's a quarter. So Lorentz invariance will tell you L mu times L mu inside the integral should be proportional to G mu nu times L square. And the proportional constant is determined by taking trace. Okay? So this is the another simplification one can do inside the integral. So therefore, all the term which is proportional to a linearly in the numerator linear L, for instance this guy, we don't need to consider because it just gives you 0. You understand? Are you guys following me? So since the numerator, if you use the linear, it should be 0, so you can forget about it. Okay, forget about it. Forget about it. And also, so here we can do the same thing. If you have L times gamma mu and this guy, this guy, it's proportional to linearly in L. Okay? So this cross term will vanish. L times this guy. Cross term will vanish because of this relation. Okay? So therefore, what we need to be careful is this times, this times, this time. This. And we can use this again and trick this one. Again, this one. Sorry, I think it's not that simple. Sorry, let me do that. Sorry. So where can I use? Okay, I can use here. now okay, so let's see. So now we just want to evaluate the L gamma mu L. Okay. And this is equal to L rho L sigma gamma, maybe the rho is better. Rho sigma, rho gamma mu, gamma sigma. Okay. And then we just apply the group of algebra again. So if you apply group of algebra, you get the rho L sigma gamma rho gamma sigma 2g mu sigma times minus gamma sigma gamma mu. Okay. Okay. And then, so here, what you get is that the gamma rho, gamma sigma contract with L rho and L sigma. You just have this is symmetric, so you have just G mu. So you have L squared, and then let me think. Yeah, it should be okay. And then, so this one is the gamma mu. And here, what you have is that the sigma plus 2 times L slash dot L mu. Is it okay? Are you guys following? Okay. So now we apply this one. We apply this one. So this one we apply this one, and then oh sorry, there must be minus sign here. There must be minus sign here. Okay. So because of this minus sign, and you just apply this rule. So this can be written as the L mu, and the gamma mu. And you just apply this rule, so this can be just translated by L squared gamma mu plus quarter will give you 1/2, and the L mu is turned out to be G mu, which can contract with gamma mu, which means gamma mu and L squared. Do you understand? Are you guys following? So L mu is G mu times L squared times 1/4. 1/4 times 2 is equal to 1/2. Okay? And G mu times gamma mu is gamma mu. Okay? And what's left is L squared. Okay? Therefore, this is equal to minus L squared. Minus L squared. So therefore, I would like to write this one over there. So this term, L slash gamma mu L slash, is just minus 1/2 gamma mu L squared. Therefore, I'm going to write upstairs because it's a good place to write. So I'm going to write here. This is equal to the following. I mean, the reason why I explained this one is that the homework you have to do similar calculation. E bar P prime minus 1/2 gamma mu L squared. That really comes from L squared gamma mu L squared. Sorry, not the square. L slash gamma mu L slash will give you minus 1/2 gamma mu L squared. Okay? And then just summarize what's left is that what's left is minus 1 Q slash plus z p slash gamma mu 1 minus y plus okay. So now we just, what's left is this one. So we just ignore this term. Therefore, what we have is that the minus 2m, 1 minus 2y, q minus p. Yo. Okay, so that's the numerator. And now we are going to apply. Okay, where should I go? Where should I go? I would like to, I should go here. Still number one. We are still number one, so be careful. So we just apply the following rule. P slash of u of p is equal to again u of p and u bar p prime p slash m times u bar of p. And then again we just apply. Where did I erase already? Oh, this one. We just apply this way. Then numerator. I mean, should I show that? Okay, so you guys agree that I can skip some part. Yeah, I mean, for instance, if you just apply p slash, so here p slash is here, act on u of p, will give you m. Okay? P slash acts on u will give you m, and also you can just write down this p slash here as this is equal to p prime slash plus is it the minus? Oh, sorry. Q is equal to p minus q slash. So p slash here can be written p prime slash minus q slash. Okay, and the p prime slash acts on u of p is equal to m. Okay, because of this equation motion. Okay. And then again, so bring q. You just commute q slash and gamma mu, and then you encounter this q slash. And at the end of the day, what you get is that this numerator is equal to u bar of p prime gamma mu minus 1/2 L square plus 1 minus x 1 minus y q square plus 1 minus 2z minus z square, like this way. So gamma mu term is coming from here. Gamma mu in proportion gamma mu and gamma mu. And then the first term, of course, coming from this guy. And the second term is indeed coming from this q slash. Z appear here. So minus z minus y is equal to 1 minus x. So minus y minus z is equal to 1 minus x. Okay, 1 minus x here. That's why here you have a 1 minus x here. And also here you have a 1 minus y, right? 1 minus y. That 1 minus y is really coming here. And if you commute q slash here in the gamma mu, and if you apply in the q slash here, you get the q square over there, in fact. And the same And also, as I mentioned, P slash acts on UP prime will give you M, and the P acts on UP will give M, so you get the M squared term coming from here. And of course, if you look at the coefficient, you have a Z here, and Z here, and here is just a 1 here, and so on. And then at the end of the day, you can get this. Yeah. So it's a tedious calculation, but if you do that, one can obtain this expression. And also, there's some term which is proportional to P prime P mu M times Z and Z minus 1. So this is indeed coming from the from one is coming from here. I think I missed some term. Sorry. So there must be. Sorry, I think. Sorry, I think this should be 2-0. Sorry, I think I missed something. Sorry, here, Z here. Yeah, sorry, Z here. And this is Z here, sorry. I missed Z here, sorry. That's why I just got confused. Overall factor Z here. And also, sorry, it should be plus sign. Sorry, plus sign. And plus sign, sorry. There are lots of mistakes. I shouldn't do that because it's a complicated calculation. P slash plus Z slash Z slash and Z. If you notice, you should point me out. Okay, anyway, so if you manipulate this numerator by using equation motion, what you get is this guy. And also, you have the Q mu M. So from this step to this step, you have to do a little bit algebra. So you get the at the end of the day, you get this equation. Okay? So you have, and now, so you notice that so here instead of Feynman parameter integral, so you have dx, dy, dz, x plus y plus z minus 1. So you have this integral. You have to put this numerator inside of this integral. And as you can easily see, so if you swap x and the integral, in the integral, so if you swap x and y, nothing will change. Nothing will change. On the other hand, if you look at the proportion Q mu, everything, if you swap x and y, you get a minus sign. Okay? So therefore, this term should be 0. If you want to integrate all. So this is exactly what we expect. So in the form factor, so we have a plus gamma mu plus b plus p prime mu plus c plus q mu, right? Q mu is essentially p minus p prime p. And then this, as I mentioned, the term proportional to this q mu should be 0. C equals has to be 0. And in fact, what we have expected, this term is 0. C equals 0. This is equal to q. And as you can easily see, you have a gamma mu times some factor, and then p plus p prime mu times some factor. That's the analysis of symmetry. Lorentz invariance is actually indeed correct after this manipulation. So again, we will use the Gordon identity. So Gordon identity is that So gamma mu can be is equal to so p prime plus p mu can be understood as the gamma mu minus I 2m I sigma mu nu and q mu. So you can just replace by using coordinate p prime p mu is this equation. You plug it into here, and then what's left is of the following expressions. Okay, now I'm going to use eraser and take. I'm going to write down the whole expression, and we take rest. We will take rest. And the number one is done. Okay. So number one is following. So 2 times d cube. This 2 is coming from Feynman. So in numerator, so Feynman d to the n minus 1 factorial. You need to have this one. So and the numerator is the what we found is of the times. And then plus like this. Okay, so just rewrite this p plus p prime term in terms of this sigma mu nu times q, and the cost is gamma mu. And therefore, so the term in here will change to minus 40. And then we now finish the step. Step 1. Okay, let's take a rest. Yeah, I mean, the polarization factor. Yeah. So you can contract with polarization. Of course, you can contract with polarization. Yes, yes. And also this is not, so we assume this is not external function.
So this is not
Yeah, this is internal, so it's connected to some diagonal. Yeah, so there is no.
But at least this is it should be I.
Yeah. So here I just put the IE outside.
Oh yes.
Yeah.
So we just so for this integral, we just consider the E squared.
Yeah, only this and this.
Oh, okay, I understand.
It will give you divergence. If this group becomes smaller, it becomes divergence. And that divergence is just somehow absorbed into the counter. Yeah, so you cannot measure. So this is not this is a part you cannot measure. No. When you take a trace, trace of G mu nu is essentially G mu nu.
So this
So
is
delta mu nu.
isn't this is the 4x4 matrix?
Yeah, 4x4 matrix. No, not that simple. I mean, when you take a trace, you need to lower the index. So L mu, and when you take a trace, means that you just take mu and mu are the contract group. So that L mu, which is close to L.
So only this.
Yes, you need to take the lower than
Okay.
I have a question. Why separated? Argument that it's a song why we separate?
No, I will explain later. This one I will explain later. Issue way. Yeah. I mean, this divergence really coming from the part which cannot be measured by the experimental detector. So the higher divergence coming from the part which cannot be detected by the experiment. So therefore, this divergence needs to be counted with this one. It is counted because I mean we cannot observe this divergence by detector. The part which the experiment cannot observe, the detector cannot observe will give you divergence. That should count with our divergence we are evaluating. No. I will explain later. Oh yeah. Ooh. Hopeless. Okay. Shall we resume? Okay, good. Let's resume. So number 2. So now, so we know d cubed is essentially what we have is L squared delta plus I epsilon cube. Okay. So essentially what we have is that first we want to perform d for L to pi to the fourth d cube over L squared. So this is L squared here. And also we want to perform d4 L to pi to the fourth whatever d cube. So we want to perform this one. To perform this integral, we will introduce so-called weak rotation. Because everything, weak rotation is just move from Lorentzian to Euclidean by introducing I on the time component. This is very simple manipulation. Okay. So what we have is that of course, before going on, so I just want to emphasize that this one is equal to F1. So this one will give you F1. This one will give you F1. And this one will give you F2. And then to evaluate F1 and F2, we want to perform this L integral. And to do that, we will introduce so-called wick rotation, number 2. We will go to number 2. So the reason why we move to the wick rotation, just move the Lorentz to Euclidean. Euclidean by just performing the L0 here is equal to I times L0 Euclidean, so that the metric is all minus, so minus. So that the integral of the L0 integral, whatever, what? So this Lorentz integral, it just becomes something like this one. Minus, sorry. Okay. So first of all, so this I coming from this there's a time integral here, L0, there's the L0 integral here. We receive I times L0 E. So therefore this I comes from this integral measure. And also denominator, this L square becomes minus L E squared. And I'm sorry, there's a minus sign here. Sorry, I made a lot of mistake. Minus sign here. So it's a minus L square because metric becomes minus 1 because of this I here. Okay. So therefore, minus LZ square minus delta to the m. So therefore, bring minus 1 to the front, minus 1 to the m. Then you denominate is LE square plus delta plus I. So that's the trick. So that's just wick rotation. And then the schematic here is that so in the final propagator and so on. So we know that so if you have L0, a space which is we consider the complex state place, and we have the pole at some whatever EP. Plus minus I epsilon, and minus EP plus I epsilon, and the integral is just propagator is just the integral is this cross direction, this real axis. But when you do the wick rotation, it's why it's called wick rotation. We just rotate in a complex way in the following way. So the integral is pure imaginary. So just rotate the axis of propagator, the integration of the time component momentum to the imaginary part. That's why it's called wick rotation. But it's just a move from Lorentz and Euclidean and put the I here. So no, it's nothing difficult. So therefore, and so this is generic case. So we are only interested in m is equal to 3, so we are talking about the generic case m. And then so we can just now compute the we want to compute this one. Is equal to just I over 2 pi to the 4th minus 1 to the n, minus 1 to the n, sorry, minus 1 to the n plus m, d4le squared to the n, le squared plus delta to the m. Okay, so this is m. So that's what we want to do. So after weak rotation, we want to evaluate this one. So the reason why we move from Lorentzian to Euclidean is just that we can use the spherical current. So you just put the L1, L2, L3, L4, and you just write down this is equal to R sine omega sine theta cos phi. I mean, you just move to. You can use the. Yeah. Then the measure becomes L to the fourth. LB becomes R cubed sine square omega sine theta dr d theta d phi d omega and so on. And then one can evaluate this one in the following way. I'm not going to go into detail. So I'm just write down the result of this integral. Okay. So therefore, so if you use this weak rotation, I just in the lecture note I just wrote down all the derivation in the lecture note to this. I just give you the result. So we are interested in m equals 3 case. M equals 3. After the weak rotation, one can perform the integral. L square I over 4 pi minus 1 to the m plus 1. Like this way. So just do the owner integral for Euclidean. So the way of performing integral is written in lecture note. I'm not gonna write down everything. And the important thing is that this is divergent when this is divergent at m equals to 3. M equals 3. This is clearly divergent. So this is in fact the divergence coming from this diagram. This group becomes really small, and then it becomes high energy momentum. So this divergence really comes from the high energy momentum. So now we finish number 2. Number 2 is quick. Number 2 is quick. So since we encounter the divergence of the integral, so if you perform this integral, so which means that if you perform this integral, you encounter divergence, which coming from really this momentum k becomes really big. So therefore, this group becomes shrink to the point. This is the source of divergence. So now we need to regularize this divergence by polycular regularization. So later part of the lecture, instead of polyculars, so we will use the later, so we will use dimensional regularization. Dimensional regularization. This dimensional regularization essentially was introduced by Ed Hooft in 70s. But first it's much more commonly used dimensional regulation nowadays. But let's first learn about the old technique. Okay. So the dimensional regularization is that so this is coming from UV divergence. So what we need to do is that we introduce following thing. Let's see. So if you have the propagator, something like a k square plus I epsilon. I don't know why I just put the camera speed. Camera speed out because of this one. Okay. But anyway, it's replaced by like following. So mu is the mu is called infrared cutoff. So the K1 speed is really the photon propagator here. The denominator of photon propagator. It's supposed to be massless. Okay, it's supposed to be massless. But to regularize this integral, so we fictiously introduce the mass of photon. Okay. So this is IR cutoff. The mass is the very small, so this is IR cutoff. And this lambda is supposed to be very big. So this is UV cutoff. And if you introduce, replace this denominator of the photon like this way, one can somehow regularize this divergence. That's what we'll see from now. So more practically, so what we need to do is that the following. Practically, what we need to do is the following. So you have the L square, the cube is split to the following thing. Let's see. Sorry, cube. And where the delta used to be the following. Yeah. minus xy q square plus 1 minus z n square. Delta used to be like this way. Is defined as this way. Now delta mu and delta lambda is as follows. I mean, this is the same. This is the same. Plus z times mu square. And it's the same. Lambda is equal to plus z times lambda square. Since we introduced the photon mass fixtures, photon mass mu and lambda, so this delta, after introducing final parameter, this delta has a dependence on mass mu and lambda of the fixtures mass of the photon. Okay. So that's what we have. So if you replace this one, now of course, I mean, if you take lambda goes to infinity, this property you can ignore, right? You can ignore. And if mu is 0, if you go to mu is 0, you can replace this one, right? So this sounds like it's a legitimate operation. Do you understand what I mean? Even though you introduce fixtures like the photon propagator, if you take lambda goes to infinity, this will go. But if you take mu goes to 0, it reduces to the original propagator. So therefore, so this procedure is kind of reasonable. So let's accept this somewhat reasonable operation, which is called Pauli Wheelers, and just do the performance integral. And this one can just again you need to do the wick rotation and replace this variable. And then what we have is at the end of the day, what we have is I over 4 pi square, and then delta mu infinity x minus delta mu square x cubed like this one. Essentially use this spherical coordinate of the Euclidean, 4-dimensional Euclidean space, then perform all the angular integral, and then what you get is this one. Yeah, often, so here as you can easily see, so L square is only depends on radial coordinate R only if you go to the Euclidean space. That's a So therefore, the integral of spherical coordinate, it just gives you the volume of three-dimensional sphere. Okay. Sorry, is this three-dimensional sphere? It should be three-dimensional sphere. Yeah, three-dimensional sphere. So if you perform this, the volume of the spherical integral, coordinate integral, so you get the volume of S3, which is 4 times pi q. I don't remember. So let me think. Is it 4 times what? Since this is 4, right? And what's left is pi squared. So for it should be 4 times pi squared. Yeah, 4 times pi squared. And then, so what's left is radial coordinate integrals, and then radial coordinate integral like this becomes like this. Okay. And this one can be performed very easily. In fact, so what's relevant is the leading one of this numerator. So leading one is x squared, right? X squared cancel with x cubed, you have 1 over x. And if you do the integral 1 over x dx, what would you get? Log. So therefore, what you get is I over 4 pi. And the subleading term indeed cancel if you honestly perform the integral. Square and log delta lambda delta mu. Okay. So now you can see. So here we know that the m equal to 3, this is divergent. Divergent, okay? This is divergent because of this term. And this leading term will give you indeed delta lambda. When lambda goes to infinity, becomes also, this term is also divergent. Okay? But we just set the lambda, it's just some cutoff. So therefore it's regularized. So that's why it's called Pauli-Biller's regularization. And Pauli-Biller's are name of physicists, of course. And then since we are looking at the leading divergence is always log divergence. Log divergence. But if you set the m equal to 2 and so on, m equal to 2 and so on, this term will give you so-called linearly divergent, and this is quadratically divergent and so on. So log divergence, essentially you have a log lambda. Divergence log lambda. You can have a linear divergence and a quadratic divergence and so on. Okay, if you go to the lower end, so you have the divergence become much more severe. That's what it means. Log divergence is a kind of mild divergence. But if you go to power row, the divergence must become much more severe. That's what it means. Okay. So now so we know this, so for m equal to 3, the next, after m equal to 3, this is the finite. Let's check by Pauli-Biller procedure. You can do the same thing. Many people have such a cold. Take care. This is called what is it called? 保重健康. So now we are looking at this one, m equals to 3. And this is equal to, in fact, yeah, I mean, it's just very simple. I mean, if you just reduce the radius, so radius integral become like this way. So let's only look at the dr integral become like this way after. And if you perform this integral, minus I over 2 4 pi square 1 over delta mu minus 1 over delta lambda. So now second term, once you take lambda goes to infinity, it drops out, and you get the finite contribution. Okay? This finite contribution, therefore, the integral, just naive integral, is also makes sense. Okay. So now we have the divergent term and then this finite term, and they just plug that one into here. Okay, and then we'll see what's going to happen. Where should I write them? Maybe next word or downstairs? Should I write downstairs? That's right here. Okay. So now they plug this result into here and just therefore this vertex u bar p prime delta gamma mu u of p can be written like a 4i e square and then minus I 2 times square, and then you have final parameter. So we now already performed this DL integral. So what's left is the integral of final parameter, x, y, z. So x dz delta x plus y plus z plus 1. And now we have this very simple, way simpler than before. Gamma mu log delta lambda delta mu plus 1 minus x 1 minus y q square divided by delta. So the first term really coming from this part, this integral. The second term is just this integral will give should be proportional to log divergence. And the second term is just a multiply 1 over delta mu and some overall factor I already factor out outside the integral. Okay. So and this is, as I mentioned, will give you F1. So the feature with F1 has a UV divergence. Okay. And then plus so that's the result. So here there's no integral there's no dependence on L. So you just use this result, and then you just got to have a 1 over delta mu in here. So that's, and we know that this one will give you F1 of Q squared, and this is F2. Now, so we did, okay, so we're now finished number 3. So now how to deal with this divergent term. So that's now a renormalization. So as I mentioned, this divergent term coming from the really high energy momentum and then the hour scale. And then the high energy part, you cannot insensitive, experimentally insensitive. And then, as I mentioned the last time, so Z1, Z2, Z3, 1/2, Z0, I call it E prime, and this is equal to Z1 times. And this one can be understood as that the here. Sorry, am I correct? Did you write it down? I just a bit confused. I think it should be okay. Yeah, it should be okay. So now, this relation can be translated into the language of this electron vertex of gamma mu of q equals to 0 can be understood as a d1 times. So d1 times this one can be understood as a gamma mu. So this red relation can be understood as the here actually you have electric charge of the gamma mu should be multiplied by the physical electric charge, and the gamma mu this is the original gamma mu should be multiplied with E prime, and we can use this relation to regularize this this F1 part. So as I mentioned, this is F1 and this is F2, and using this relation, we can just regularize the this integral. So this means that the so F0 can be understood as that the did I write the okay good. So here delta has a dependence of Q squared. So therefore, if you write down explicitly F1 0, as I mentioned, so this F1 Q squared. And then F1 Q squared. So the only F1 has the divergence. So the F1 of 0 can be understood 1 plus alpha over 2 pi. And then 0, 1 dx dy dz delta x plus y plus t minus 1. And then, so delta lambda, when you lambda goes to infinity, so you can ignore the rest of the term, because I mean the rest of the term is very small. So that what we have is that the sorry, am I making a mistake here? Why is it proportional to x? Yeah, I think I make a mistake. So what we have is that the log of c lambda square, so there's a typo in the lecture note, 0. So delta depends on q square. So then put the q square equal to 0 here. And plus 1 plus d square minus 4d m square divided by delta mu d. So this is 1 coming from just an ordinary classical level 1. It's gamma mu. Just this 1 is just a ordinary Feynman rule, and the alpha is the just really the one loop diagram we are now evaluating. And we set the q square equal to 0, which means that we can ignore this term. Q square equal to 0, we can ignore term, so we just need to care about this. That's why we have this term. And log divergence this time. So now we need to set that so what this means is that so as I mentioned, so the d1 can be written 1 plus delta 1, and then here you can write down gamma mu plus delta gamma mu is equal to gamma mu. So of course this term will give you just ordinary gamma mu. Delta gamma mu is this times gamma mu. So therefore, what we have, if you only look at the leading order of alpha correction, so this depends on alpha correction, and this depends on alpha correction. Alpha is of course structure constant e squared divided by 4 pi squared. Then if you only look at the lead of the should be yes. Yeah, I think times gamma. So therefore, so this delta mu, delta 1, this is counter term is indeed 0 when, I mean, it's a confusing, this alpha is not the same as this q squared. Okay, so let's erase alpha now. Delta 1 of the counter term should be equal to delta gamma mu of the when q squared equals to 0. Should be equal to 0. And what we are interested in that the difference between so therefore we are interested in the following quantity. So this means that the delta 1 is equal to minus this f1 0 when q squared equals to 0. So sorry, q squared equals to 0. So this means that the counter term of z1 is equal to minus f1 0. And this term has a divergence. And what we are interested in the difference between the actual so the f1 renormalized of q squared is indeed equal to 1 plus delta f1 q squared plus delta 1, which is equal to 1 plus delta f1 of q squared minus delta f1 of v. So what we are interested in that the difference between delta f1 q squared minus delta f1 z. So this is called renormalized. And if you just plug this one into here, and what you can see is that this one is equal to 1 plus alpha 2 pi 0 1 dx dy dc delta x plus y plus c minus 1. And then we will have log of delta mu 0 plus 1 minus x 1 minus 1 e squared divided by delta mu squared plus 1 minus z squared minus 4z and squared divided by delta mu squared. Not yet. Minus okay, I think what I should do is at the point. Like this. Okay. So this has a divergent part, this has a divergent part, and this also has a divergent part, but difference is fine. Do you understand what I mean? So here there is no divergent part. This has a divergent part. This has a divergent part, but difference is fine. That's the meaning of renormalization. Let me give schematic idea. So what we did is, okay, so space of, so the momentum k, okay, and k equals to 0. Or maybe q is also okay, q, say q. What we did is that if you integrate over everything, so if you integrate over everything, okay, from very high momentum to 0, q squared, okay, let's call q squared. Q squared is better. Q squared to 0, that will give you delta, sorry, delta F10. Okay, delta F10. On the other hand, if you have a Q square, so here, let's go Q square. If you integrate everything over here, from high momentum up to the Q square, you will get delta F1 Q square. Because of high momentum, both have this log divergence, log lambda square divergence. However, if you take a difference between this orange one to purple one, the answer is finite. Okay? That's the meaning of renormalization. So therefore, what we are interested in the difference between these two. Okay? We started with very low energy, and a little bit you just increase the energy Q square moment. The dependence of this form factor is really finite, and it's a function of Q square. Okay? It's a function of Q square, and it's finite. So if you look at the difference from 0 to Q square, the difference is finite. We don't care about the rest. That's the meaning of renormalization. Do you understand? And this difference is everything absorbed in delta 1. Okay? Delta 1 is equal to minus F1. So therefore, what we did is that the usual axial vortex gamma mu Q square minus delta 1. Plus, okay. The sign of the plus delta 1. Okay? All the divergence is absorbed into this delta 1, and what's left is the finite pieces. So that's the idea of the renormalization. Okay. Any question at this moment? So as you can easily see, so this delta F1 is equal to minus delta 1. Okay? So therefore, this purple one is equal to minus delta 1. The purple one is everything absorbed. The divergence part in absorbed in the counter term, and what's left is the difference between delta 1 and this delta F1. And we are looking at only the dependence of Q square from the bottom, not from the up one. That's the meaning of renormalization. Okay, now we are almost done of renormalization. So we are almost done of renormalization. And now we know the anomalous magnetic moment is proportional F to 0. That's I already explained at the beginning of the lecture. And let's evaluate F to 0. So as I mentioned, so F to 0 is really F to 0 is this guy, is indeed the finite. So we just need to perform this integral. And that's what Schwinger did. Even though we could finish this computation within like 2 hours, 2.5 hours in this lecture, because of a very sophisticated technique, Feynman, parameter, weak rotation, polyvariate regularization, and so on. Anyway, but the Schwinger did much more involved computation, like much more involved. That's why it took a long time to get this result. Okay, so F2 is just integral I already erased the outer. Okay. The outer when q squared equals 0, so this f2 0 is indeed alpha over pi 1 over 0 dz dy dx. What I'm thinking? What's it? Y plus c minus 1 c over 1 minus c. So this is indeed f2 0. In fact, so let's check the f2 0 delta. What was the delta? Okay, good. So delta mu 0 is indeed equal to 1 over z square m square. Therefore, they square cancel, and z 1 minus 1 of the factor 1 minus z cancel. What's left is this one. And you have to be careful about normalization. And that's what we have. And then I'm not going to do the computation. Everything, the lecture notes is given, so you can just perform this integral so easily. So it's super easy. I'm not going to do the calculation. Or do you want me to do calculation because it's the last step? I mean, I don't think it's meaningful to do the calculation. Yeah, it's a meaningful. So this will give you alpha over 2 pi. I mean, this is super easy. I have written all the steps in the lecture, so it's you can just follow. Okay. So therefore, so as I mentioned, g is equal to 2 times 1 plus f2 0. And then, so therefore, g minus 2 divided by 2 is equal to f0, which is alpha over 2 pi. And this is equal to 0.0011614. And this result was obtained by Schwinger in 1948. 1948, as I mentioned many times, Schwinger. And this is an anomalous magnetic moment and the actual value. So this is the at one loop. And then this anomalous magnetic moment, experimental, is, as I mentioned last time, 0.001157. And then it's a miraculously close. And the difference is just a difference between them is just a we just only divided one loop. If you divide it to 2 loops, 3 loops, it's getting closer and closer. Okay. So therefore, even though it's a finite, so we know that F1 has a UV divergence, F2 doesn't have a UV divergence. But it's a finite, but there is some contribution coming from quantum effect here. So you can easily see. So the quantum effect is alpha over 2 pi to the anomalous magnetic moment. And then you have a slight shift in the, which is different from the prediction coming from the Dirac equation, which is ordinary Dirac equation. Okay, so this is one of the milestones of the quantum field theory in the early 20th century. I will say early 20th century, sorry. The first half of the 20th century. Okay, next, we are going to talk about, again, F1. So this F1. This F1. And this has so-called infrared divergence. So we understood how to regularize F1 Q square has UV divergence. UV divergence. UV divergence. And this was regularized, renormalized by introducing into so-called counter term delta 1. Essentially, you just delta 1 has the infinity and delta F1 has an infinity. If you counter them together, you get the final term. That's what we have. But unfortunately, this also has IR divergence. Also has IR divergence. Coming from this mu square. Unfortunately, I don't have so much time to explain it. Okay, so let me briefly explain rough start. So if you look at this renormalized term, then set the mu goes to infinity. No, mu goes to 0, sorry. Delta delta F renormalized Q squared, and set mu goes to 0. So it has a following divergent part, something like F1 alpha over pi FIR. This depends on P and P prime, and then log minus Q squared mu squared. If you take that expression and mu goes to 0, it has this kind of divergent part. So if you set mu goes to 0, it becomes infinity. Okay? But this one, indeed, is not problem also. But this is not the problem, so I can now reverse here. There is some contribution. So there is so-called soft bottom. So there is some vertex P and P prime and Q, and there is some the electron. If electron is moving, it can emit so-called the soft bottom when K is very small. K is very small. So this is called soft bottom, people. You can emit this kind of photon like this one. And in fact, when the observatory momentum K is very small, the experimental detector cannot observe, cannot detect. Experimental device cannot detect the soft photon if the energy is too low. And if you evaluate this contribution for very, very soft photon, what you get is the following. Pi r, and I think did I call it? I think this I call it Q squared. Sorry, this one also depends on the Q squared. Q squared, and then log of mu squared. And I have to be careful about sign of the sign. Okay, so let's see the minus. I don't know which one is minus. Anyway, it depends on how you define FIR. So if you evaluate the contribution of this soft photon, it also, the E minimum is the energy level the experimental device can detect. If the energy of the photon is low enough, less than E minimum, so experimental device cannot detect these photons. But we have to take into account this kind of effect, even though experimental device cannot detect. So the contribution is really this one. Mu is the IR cutoff again. If mu goes to 0, this is also divergent part. But if you add them together, this mu cancel with this mu cancel because of the sign. And at the end of the day, so what you get is so this has IR divergence, then these two terms have IR divergence. If you add them together, what you get is that the alpha over pi FIR Q square and log minus Q square plus E minimum square. So now for E minimum is the energy level the experimental device can reach. Okay? So in the observation now level, there is no IR divergence because this mu square, log mu square, and log mu square cancel. Even if mu goes to 0, nothing okay, no problem at all. Because I mean we have the limitation of the experimental devices. We cannot go beyond. Okay. The some energy level. So therefore, it's regulated by experimental limitation in some sense. So these IR divergence of F1 here, we normalize one, is essentially they cancel with these two diagrams. That's what I'm going to explain at the beginning of the next lecture. And this is called what is it called? I cannot. These two diagrams is the diagram called Gram-Ström. Gram-Ström essentially means that if you have the if you have atoms, and then if you have electrons, it's just that because of the charge, it has a charge, and the electron have a charge, so the electrons accelerate, and then it just emits some photon. Because of acceleration, it emits the photons. And electron becomes like the speed of electrons become, or energy of electron becomes decreasing because it emits a photon. And the decelerating. So this is called Gram-Ström, and the origin of this term is, of course, as you can easily see from the word is German, and the Bremsen. This Bremsen is called brake. Brake means of course, as you know, I mean, brake is the car, you have a brake, right? Brake. And the Strahlung is the radiation. So by emitting radiation, it's a decelerator. That's what it means. Anyway, so let's stop here. And at the beginning of lecture, I will explain this calculation. And then we'll move on to evaluating Z2. Today, I've already done Z1, next Z2. Okay, let's stop here. Integration range. So you just integrate from high energy to low energy. So you just do the DL. with this discipline. So you just create just integrate from high energy to low energy, everything, all the momentum. That's the problem. Yeah, Pittsburgh. Gamma, mu. Oh yeah, because it's fine. Yeah. We are now interested in only like
They're kind of why you have to use a really kind of diverse.
iron divergence. Yeah.
Also, calculate
What do you mean? I mean, here we cannot observe this experiment when K is low enough. But there must be some contribution. That contribution cancels with this contribution from iron.
什么都熬夜的问题。那我认为是需要去进思识。你不能把什么都弄没了。像我从来就是你知道的时候，为什么我别靠你们到？
The radiative of this particle radiative of this is calculated.
如果你的睡觉是其实什么时候睡这个并没有区别。这些看阳是看阳光，不知道。
I know how to do it. String.
对啊，但以后是等于这，因为这样
So calculate this thing. Why we have to have some
因为阳光会
radiation
影响你的
process?
睡眠。
对的，阳光会影响。
但是只要你够黑，或者是
你不晒阳光，阳光
We cannot
你不晒阳光，你跟说在。
the
你封闭阳
low
光。
energy momentum.
你想光。
So therefore, all the low energy
那就像
momentum
我们一起早点睡，
of
你
the
不学
photon should all
那你敢不敢这么说？你敢这么说，我就敢这么说。那你每次都说有问题，但是你每次。
The radiative this term is diverse. What we can't just calculate the matter of this radiation and we gather diverse results is definitely not right.
what?
Yeah, just there are two terms. And this diverse, the sum is not there.
Yeah.
Yes, so we can make an experiment. We can do a measurement. We suppose there is something like that, and we get all the light, all the radiation, and so we can only measure this part, and which is diverse. I'm sorry.
not divergent. If you do the measurement, it doesn't matter.
So why do you measure it is not divergent?
So you cannot distinguish these two processes.
Why we can't distinguish this process? This process seems to be like,
We cannot distinguish this process.
the scheduling process is localized.
No, we only look at this one.
This is realized, and this is not realized.
Yeah, that's true.
So we can just measure real
Yeah,
time.
yeah.
So why do we measure both sides?
What do you mean? But
So the basic question is why we can't just
no, if you just have a real one, if you can measure, it's not divergent.
Yes.
It's not divergent.
I can't understand why.
Because the divergent part is the part which cannot be measured.
Why it is can't be measured?
That I mentioned that really coming from the IRWs which is lower than the energy level, which cannot be detected.
Oh. But there is still a nuclear.
Because I put to regularize divergence. This mu is lower than E minimum, so you cannot measure. So this divergence cannot be measured. Why? We here this divergence we are estimating the amount which cannot be measured.